I want to talk about superposition, and particularly how I talk about linear circuits and solutions of superposition. What's interesting of any linear system you would come up with, what you realize is that just a very simple relationship is that if I have a linear function, then I know that any sort of weighted sum of different things in that is really going to be, that constant coming out, again, constant A and constant B, is really going to be a constant times the first function plus a constant times the second function. And this sort of additive property is very, very important. And you're probably familiar with linear functions from many different places. Could be from solutions of linear systems. Could be from derivatives and integrals, which are linear functions. And they follow along these lines. So if I have elements x and y, I'm basically taking an integral of each of them separately and adding. Well, it turns out for circuits I get kind of the same idea, particularly if they're linear circuits. I get exactly this result. And you think, wow, that could potentially be kind of useful. And there's many different cases and examples where that works. And you can imagine having many different effectively different pieces of a solution all being together. This is talked about as superposition, is that I have many different solutions all writing together. This happens anytime I have a linear system. You could talk about this in both linear circuits. You could talk about this function in optical systems and optics. You could see this in terms of quantum wave functions. We could go on and on about how this concept of superposition shows up in many places. Certainly, if I have nice continuous value things, it tends to behave nicer, but it's not even a requirement there. So what it allows me to have is multiple sources and multiple things all kind of happening together. And so what does that mean for a circuit? And it's actually best, although this is nice and theoretical, the right way to think about this is to get more into what happens if I take a practical example and I look at the circuit, and I like to solve this circuit in a couple different ways, and so I figured I would try this, also show it here. What you end up finding out is that, well, okay, what if I were to then solve the circuit with just V1 and turn V2 off, and then use adjuster V2 and turn V1 off? Well, that does simplify the circuit, and I could then take the results and just add them. Now, it might be rather messy, but it does give me a very nice direct solution if I'm doing this. And so one way to approach this, and again, it's always trying to make sure that math is right in a case like this. So I hope that as I look at this a few months later, I didn't make any errors on this. But what you find is that if I take this one, I turn it off, I'm going to look for E1 and E2. Turn this one off, a couple things come out immediately. One is that R3 and R4 are in parallel. So I can immediately simplify that. They're in series with R5, which means in terms of equivalent resistance, I see an R5 plus parallel R3, or R3 parallel R4. And that sits in parallel with R2. And so this allows me to talk about E1, there's a certain voltage divider. It also tells me that E2, there's a voltage divider from E1 because of this R5 plus in this parallel combination. So you can kind of see this in the math as we put it together. Similar thing for V2. Everything kind of flips around, but now I'm kind of looking at V2 and this is 0. So these two start in parallel. I see the R1 and R2 parallel here, plus R5, and I can work through it equivalently. What turns out then is if I want to say what is the final solution for E1 and E2, well, all I need to do is add what was E1 here and what was E1 here. It does get a little messy. Just take this and then take this one and plug everything in, and it's a little bit messy in this case. E2 is, and same thing for E1. Now I could likely do a lot more simplification, and you really can kind of simplify this and get better and much clearer results. That's not the point of where I'm going over here. What I want you to be able to see is that I could do this. And imagine if those resistors were like, say, all equivalent or nearly equivalent. There's probably a bunch of things I can do to reduce this. So it's an opportunity and a possibility anytime I need to solve circuits like this. And so it's a very powerful technique. It shows up often in places where the circuit just looks really tough to handle, but I can kind of make this work. The other thing is that superposition, of course, will handle if I have any dependent sources. But I don't get to turn those off. I mean, I have to keep those on through the whole solution. So I could turn any independent source off, or have any linear combination of sources on. I could have like plus and minus, and I could do anything there, and it would still turn out to give me a solution I'm looking for. So it's very important to keep all of these options available when you're doing circuit analysis, because any given circuit, one may actually speak to you, it may actually give you the right answer, it may actually help you solve this much clearer.